A random sample of 13 professional athletes produced the following data, where X is the number of endorsements the player has and Y is the amount of money the player made in millions of dollars. Okay, so we have two sets of data. X is the number of endorsements, Y is the millions of dollars the player made. Okay, we have the same data here, separated by columns already, make it a little bit easier to copy and paste the data. We want to perform a hypothesis test with a 3% level of significance to determine whether or not there's a significant linear correlation between the number of endorsements an athlete receives and the amount of money they make. Okay, so since we're testing to see if there is a significant linear correlation, we are conducting a hypothesis test about the population correlation coefficient, rho. The null hypothesis is that rho is equal to 0, that there is no linear correlation. The alternative hypothesis is the opposite, that rho is not equal to 0. If rho is not equal to 0, there is at least some degree of linear correlation. Doesn't have to be a whole lot, but there is some statistically significant amount of linear correlation. Because the alternative hypothesis uses a not equal to symbol, we will be performing a two-tailed test. We want to look in the left tail, we want to look in the right tail. Both sides are away from 0. Both sides are not equal to 0. So we want to look at both sides. We want to do a two-tailed test. Okay. So now that we got step 1 done, we've identified our hypotheses. Let's, assuming the null hypothesis is true, let's identify our sampling distribution. So for a test of the correlation coefficient, we use a t-distribution. With n minus 2 degrees of freedom. Okay, so t-distribution. And we have, let's see, we have data from 13 professional athletes. So 13 XY pairs, which means our n is 13. So 13 minus 2, that's 11 degrees of freedom. Okay. All right. Now we are ready to find the p-value. We are going to start by first identifying our correlation coefficient r. So let's find that correlation coefficient r. So for this, we'll need our calculator. I'm going to move my data into the calculator so I can reference it. So I have two lists of data here. I have x, which is the number of endorsements. I'm going to paste it in here so I get a list. And then my other data is the millions of dollars player made. That's my y variable. And I want to paste that in here, so let's copy that first down here. So I'll highlight it, I'll copy it, and I'll paste it here so we get that list of data. Okay? And then define my sample correlation coefficient r. I'm going to use the core function, short for correlation, and then just plug in my x and y. Okay, that's going to give me my correlation coefficient r. That's 0.7265799. Okay, so just let's do a little sanity check of what that means. What does a correlation coefficient mean again? Remember, if it's positive, that means the data is positively correlated. If our correlation coefficient is negative, it means our sample data is negatively correlated. In this case, this is positive. So if there is a level of correlation, the best fit line would go uphill, going from left to right. Okay. The closer the correlation coefficient is to 1, the stronger the level of correlation. 0.7265, that's certainly closer to 1 than it is to 0, right? That's a fairly strong linear correlation. Now, it doesn't, whether or not we accept the null hypothesis or the alternative hypothesis, doesn't depend only on our correlation coefficient, but also how many data points we have, right? If we only have, 3 data points, maybe we got lucky and all 3 are very strongly linearly correlated. But the more data points we have, the more likely our sample data is to be a good reflection of our population data. Okay, so we need to take that into account too. Okay, so we want to calculate the probability that R has some relationship to our actual sample correlation coefficient. In this case, we want that to be greater than or equal to. We're going to start by looking in the right tail, the tail that this value is closer to. Okay? Whenever you do a two-tailed test, you start by looking in the tail your value is closer to. Since the center point of all possible correlation coefficients is at 0, and this is a positive number, this is going to be closer to the positive tail, or the right tail. And so I'm looking for the values that are greater than or equal to this. Okay? Okay, now we want to find the test statistic for that correlation coefficient. So we're using a t-distribution, so I'm going to use a t variable here. Okay, remember that correlation coefficient, the formula is t equals r times square root of n minus 2 over square root of 1 minus r squared. Okay, so let's get all that together. We already have r here. The only other value that I need is the n. Now we've already found that, right? N is 13. I could either do n equals 13, or I could count how many data points we have in one of these lists, doesn't matter which one, and that might just be a good check to make sure that we've copied everything. It looks like we did. Okay, we have 13 data points in that list. All right, so I have my r, I have my n, we have everything we need to calculate that test statistic. So t is equal to my sample correlation coefficient r times the square root of n minus 2 divided by the square root of 1 minus r squared. And all I'm doing is I'm taking this formula and re-expressing it in the calculator. So the calculator will calculate the value of it for me. Okay, so let's evaluate. Let's get that t-score. And we get 3.507285. So I'm going to plug that in here. I'm going to make sure my inequality symbol stays the same. Okay, so what I'm looking for here, graphically, is if here's my t-distribution, make that a little more even. That's better. Remember the mean of a t-distribution 0. We have 3.507285. That's pretty far over here. Okay, that's way over here. And so I'm going to start by calculating the probability in the tail I'm nearest to. Okay, so we're going to start by calculating that probability. To calculate probability of a t-distribution, I'm going to use the pt function. I give it my quantile value, which for a t-distribution is the t-score. And since it's a t-distribution, I also have to specify the degrees of freedom, which is 11 or n minus 2. Okay, 2 less than the sample size. Now, this would give me the probability to the left of this t-value. I want the probability in the right tail, to the right of that t-value, to the right of 3.507285. To calculate probability to the right, I do 1 minus the probability to the left. And so the probability I get is, there we go, it's 0.0024534888. Okay, so let's get that, and put it in the answer box. Now this is the probability we calculated, but it's not the full p-value, right? We are doing a two-tailed test. That 0.02453488, that's the probability just in this right tail. But I want to count the probability in both tails. So I want to find the mere probability in this tail and add it in. Well, because there's this symmetry and because the probabilities are the mirror of one another, if I take this probability and this probability together, it's just going to be twice the probability that's just in this tail. That's always how two-tailed probability works. So I'm just going to take this value, multiply it by 2. that will give me my p-value for this two-tailed test. Okay, so I'm going to take this guy, and I'm just going to multiply by 2. And that will give me my full p-value, 0.004906976. That's the p-value. Okay, so now that I have the p-value, I want to compare that p-value to my level of significance alpha. So let's grab that level of significance alpha. What was it again? It was 3%. Okay, so I want to convert that to decimal form. 3% is 0.03. And now let's compare alpha to our p-value. In this case, notice the p-value is smaller. It's got 2 zeros in front of the 4, whereas alpha just has 1 zero in front of the 3, right? So the p-value is definitely smaller, and it's quite a bit smaller, actually. When the p-value is smaller than alpha, that's when we reject the null hypothesis and instead accept the alternative hypothesis. Okay? The alternative in this case is that the number of endorsements a player has made and the amount of money the player has are correlated. Okay? Since we're rejecting the null hypothesis and accepting the alternative, we want to conclude that the alternative is true. We conclude that these two data values, these two variables, are correlated. Not just with the sample data we have, but in the entire population. So let's submit, and we have it.